Okay, so the next thing is we just learned about potential energy, so let's look at kinetic energy. So in the past we learned that the equation for kinetic energy is the following. Ke is equal to 1/2 mv squared. So what we can see over here is that, first of all, we know that for an object to be moving in a circular orbit, we know that the force of gravity, Fg, must equal to the centripetal force. So again, before we move on, this equation we're going to derive for kinetic energy and total energy only works for an object that is in orbit. If an object is not in orbit, if it's just flying through space or just moving like a car traveling on the road, or an asteroid or a comet that's just traveling in space, that's not in a circular orbit, we cannot use this equation because this depends on the fact that centripetal motion is involved. So what we can see here is so we have force of gravity is equal to the centripetal force. One of the r's cancel out, we get gm over r is equal to mv squared. But then notice this mv squared, that looks awfully similar to right here, mv squared. So we just multiply both sides by half, we actually get an expression for kinetic energy. So kinetic energy ends up being just gmm, so the masses of the two objects multiplied together, multiplied by capital G, divided by 2r. If we scroll down, we can solve for an expression for total energy as well. You know, total energy is the combination of potential energy and kinetic energy. So our kinetic energy equation was that we just found that gmm over 2r, and potential energy, that's given to us on the formula sheet, and we also derived that earlier. We have that to be negative gmm over r. So when we add those two numbers together, we get an expression for total energy, negative gmm over 2r. Again, we're going to have a negative value for total energy. Again, it doesn't matter if it's negative or positive. Like, the question is really, what is energy? We don't really know in itself what it is, but we know we need it to do stuff. So what's always interesting to us is that change in energy. However, we can quantify total right here as well. So what is the kinetic energy and total energy of an object with a mass of 250 kilograms if it is in a circular orbit of the moon at a distance of 5 times 10 to the 6 meters from the center of the Earth? So a key thing to note right here is it's in circular orbits. So that means we can use the two equations we just derived. So kinetic energy is equal to gmm over 2r. So we plug in our values, 6.67 times 10 to the negative 11 multiplied by 7.35 times 10 to the 22 kilograms. We're talking about the mass of the moon. And the object in orbit is 250 kilograms. And that's divided by 2 multiplied by the distance, 5.0 times 10 to the 6 meters. Or it's always the distance from the centers of the two objects. So you get a value of 1.2 times 10 to the 8 joules. Now total energy is just the equation negative gmm over 2r. So notice it's going to be the same magnitude, same equation. One's positive, one's negative. So that just means it's going to be negative 1.2 times 10 to the 8 joules.